Hey everybody, welcome to another Cast AI live webinar. Glad that you can join us for this really exciting topic. We're going to be talking about a fairly new innovation within Kubernetes. It just got released a couple weeks ago in the stable release channel 133. So it's about we're going to be talking about in-place right sizing of pods without having restarts. This is a pretty cool topic. So let's get Luis, let's go to the next slide and I'll introduce our conversation panel for today. So with me, my name is Leon. I'm a co-founder and CTO at Cast. I've got Luis from our sales engineering team and Yolanta, who is from our engineering team that's actually responsible for our workload right sizing products. So we'll be able to engage in a really cool Q&A with all three of us at the end of the live demo and presentation. So let's move on to the next slide. This is what we're going to cover today. We're going to do a quick introduction, a couple of minutes of Cast AI, why it matters. We're going to just talk a little bit about why this problem is important, and we're going to do that via something called our cost benchmark for Kubernetes. It's something we publish every single year, and it has some very interesting insights around where people are spending resources needlessly, where they're gaining or losing in efficiency. And we're going to use some of those numbers to illustrate the pain points around why in-place resizing is so important. Finally, we're going to talk about the actual in-place concept for pod resizing, and then we're going to do the meat of the live presentation, which is the demo, which Luis is going to help us with. So without any further ado, let's get started into that. Before we jump into the content, we want to ask folks a question. What is the biggest pain point when you resize your Kubernetes workloads today? So when you set your requests and your limits, where do you feel the most pain, operationally or structurally or otherwise? So we're just going to give everyone a few minutes to fill out the poll that should be on your screen right now. We'll show the results and then we'll dig into some details. These might be some pretty surprising results for some of you folks. So let's give everyone a minute to fill that out and then we can get started. So those pain points are restarts cause downtime or degraded service, the fact that you have to manually tune, and that's a time-consuming process, lack of visibility into real usage, the real risk of under-provisioning. I think that's something everybody is scared of, specifically around memory provisioning. And then some folks just haven't even thought about it until today's webinar, although I think that number, I'll go out on a limb and say that number is going to be pretty low. So, Alexei, are we waiting for folks to close the poll, or is we still a few straggling answers?
I think you're already done, so we can stop doing that.
All right, so let's close this out. Are we going to show the results here? There we go. So as I predicted, very few people, so zero, haven't thought about it. And the biggest pain point, and I suspect why you guys are joining the webinar today is restarts cause downtime and bad service experience, and manual tuning is very time consuming. This is pretty predictable outcomes, so that's great. All right, let's jump into the content. This is exciting stuff. A little bit about the platform. So I'll cover this in 30 seconds. Cast is an overall optimization platform. We have many components. We're not talking about security or database optimization or even AI optimization today. We're talking about one very specific capability within the platform, which is called workload optimization. One key thing to notice when you look at this kind of green flow, all of these tools work together. So that's what's the advantage of a platform. When we talk about a platform play, we're really talking about the ability for key capabilities to work together. So, for example, the things that we do in workload optimization directly impact how the cluster autoscaler needs to work, how bin packing or rebalancing needs to work, and how we integrate with spot instances or commitments. So all of these things work together to create value. But today we're specifically going to be talking about workload optimization. Let's go to the next slide. All right. So let's talk about some reality on the ground. What is the field really seeing when it comes to Kubernetes resource usage? Like what's really happening, Luis? Like let's pull back the veil and talk about some real stats.
Thanks. No, that's a great question. We do this report every year, and this year results show that a 23% drop in the CPU efficiency, especially because over provisioning. That's when people provision more CPU than really needed. And another very interesting finding of this year report is that 6% of the containers are exceeding the memory limits daily. That means that many people are requesting less resources than the application really needs. So this leads to a lot of problems, especially instability on applications and customer experience problems, right?
So let's go to the next slide, but that's pretty interesting, Luis. Like you're telling,
Yeah.
so it's counterintuitive for most people. You're telling me, so I would have said most people are overestimating the amount of resources they need, which is probably true for some types of resources like CPU. But you're telling me that people are underestimating some critical resources like memory, which is actually leading to outage. That's pretty painful. So give me a little bit more specific detail here. How can we quantify this?
Yeah, perfect. We analyze every year thousands of clusters. And here we saw average CPU utilization of just 10%. This is very, very low. That means that people are provisioning 10 times more resources than needed. Memory is a little bit better with 23% of memory utilization, but still very low. And many times people are always under provisioning resources. In this
So
case, putting less resource than needed.
So, Lewis, let's go to the next slide. And I think this is the part that's going to really show how bad over provisioning can get when we're talking about the resources that are typically over provisioned.
Yes, exactly, Leon. This is a real word container with a request of just 0.3 CPU. And we can see the blue line below with the request. And above in the green line, the real usage of the application. Look the difference, right? The real usage is just about like 0.01. And the gap that we can see here, that's what we call over provisioning. That's actually the waste, right? What you paid and you don't actually use.
Luis, it's Friday today. You're giving me all kinds of problems that I have to contend with. I don't want to hear about problems necessarily. I want to hear about some solutions. So, how do we fix this? What happens when CAS steps in?
Perfect. This is what happens when CastAI steps in. We detect the patterns in real time, the application usage. We know how many CPUs and memory the application are requesting, and we use machine learning to optimize it. But the great thing, because we have a lot of solutions in the market today that provides recommendations, and that's not our ultimate goal. We would like to optimize it, right? When CastAI steps in, we automatically adjust your CPU or memory requests to the very near of the real usage. So you don't need to edit YAML files, you don't need to do any manual work, and you can save a lot of money that you can invest in other stuff.
Okay, but Luis, hold on a second. I feel like you did a little bit of a switch and bait on me here because remember at the beginning of the conversation we were talking about the problem with downtime with respect to memory under provisioning. This is great. You're going to save me money, but if if my app is crash looping all the time due to kills, that doesn't help at all. So what do we do with memory?
Yeah, perfect. This is what we're going to cover in this slide. And this now is a very, very interesting example. It's a real world example. We can see here in the right, in the left, the real memory used by this application. The application is using around 3.5 gigs, and the request here below is only 2 gigs, right? And one very interesting pattern here is the peaks and valleys that you can see here, right? What this represents in this case, the application was crashing with OOM kills a lot here, and that's why we can see like these peaks and valleys. This represents the application crashing. Here in the right, we can see exactly when we activated our workload optimization. We detected all of this data and how much memory it's really needed. And we started adjusting. We adjusted like 3 times here until we find like a better utilization and stability here. So you can see the real difference. You have like a much more stable line on the memory used, meaning that application is not being affected or restarted anymore. And of course, the customer in the end is not being affected anymore.
Okay, so this is really interesting, and I just want to double click on this concept for a second. You know, when we talked about CPU in the previous slide, CPU is a compressible resource, meaning if you have two pods that are contending for CPU, they might suffer some performance issues, but they're not going to crash. Memory in Kubernetes without swap space is non-compressible resource, meaning if you over allocate, two pods are using more than the total physical memory available, one of those pods is going to feel memory pressure and it will have to restart. And that's a terrible outcome. So what you're showing here is kind of the remediation of both on the first slide, waste through the real-time adjustment of CPU requirements, and then better performance and uptime and availability as a result of better resource optimization for memory. But let's switch gears a little bit. Let's go to the next slide. Why are we here today? Tell me what is in place pod right sizing? Like, what is this thing and why does it matter?
Perfect. Traditionally, before Kubernetes 1.33, to make any adjustment in CPU or memory requests, they required like a pod restart. And now with this new feature called in-place resizing, that means that you can adjust the resource live without restarting the pod. This is very important for, especially for dynamic workloads or applications that cannot handle restarts well, or even applications that have a lot of spikes, such as Java applications. Java applications specifically because many services needs a lot of resources to restart, and a little bit after it starts to stabilize, right? So doing this without any restarts right now, it's a huge game changer, especially in these cases.
Yeah, so with Java workloads specifically, I think you're talking about the cold restart problem, right? So if anyone's ever written a Spring Boot app, you do a lot of like depending on the ORM you're using, you do a lot of cache warming, read a lot of records from the database to pre-populate things, and that takes time, and that cold start is very painful. So like you almost don't want to start restart Java apps for that very reason because they take so long to get registered with the service. It's kind of an anti-pattern. It's not an anti-pattern, but it flies against the grain for a lot of what we're trying to achieve with microservice architecture. So, but what else? What other problems can we cause with pod restarts? I think maybe let's look at the next slide and talk through some of these
Yeah,
problems.
yeah, plenty of problems, especially I can say downtime. It's a little bit obvious because when we restart the pod, if your application is not fully prepared to handle this, you'll have downtime for your customers. You are going to have like some degradation in your service. But I also can say about like operational complexity. When you talk about optimization, in our real world experience with customers, the operations teams and necessary teams get a little bit crazy because this can lead to manual work or even a lot of alerts in their systems when it leads to starts. And of course, the teams over provision a lot to avoid the risk, right? And now, without needing to restart frequently the application, they can not over provisioning too much and think about this risk.
Okay. So that makes sense. And Kubernetes provides Kubernetes provides a bunch of capabilities that help us mitigate the risk, right? So we talk to our customers about pod disruption budgets as a mechanism to drain nodes without bringing all of those pods down at the same time. We also have capabilities like rolling restarts when you roll a service to restart it. It can roll gradually. You can do green blue deployments. And those are all Kubernetes native concepts. And now Kubernetes is providing in 1.3.3 this inline mechanism for pod resizing. So who makes the decision to resize though? That's not a native Kubernetes capability, is it?
Yes, Kubernetes gives you just the engine, and here CastAI adds all the intelligence and the driver with our workload autoscaler. What we do, you can define some scaling policies to apply to your workloads, defining some constraints or some information on how you want CastAI to behave. CastAI keeps monitoring your workloads in real time. And when we detect this under provisioning or over provisioning events, or at least, for example, out of memory queues, we do the adjustment immediately, right? It's at the same time. And
Okay.
now with the in place.
So sorry, Luis, I just want to make sure I understand this correctly. Like let's be very clear with the folks on the call. The Cast platform is making the decision as to the right size of the pod, also taking into account your horizontal scaling strategies, right? So if you have HPA in place, whether it's cast HPA or native HPA, it doesn't, or CADA, it doesn't matter. We're taking all that logic into consideration when we make these right sizing recommendations, right? So we're doing that for memory, we're doing that for CPU, we're taking into account spikiness in workloads and seasonality in workloads. And now what you're saying is we have this added advantage of leveraging the Kubernetes capability to make those adjustments when without restarting the pod, which I think is a huge help, right? It relieves a ton of operational complexity. So that's amazing.
Exactly.
Uh, I
Exactly.
think I think folks are just dying to see this. So maybe let's jump to the next slide. Let's quickly cover this. Like what happens, what's the outcome, and what are the trade-offs, and let's show folks how this works.
Yeah, perfect. Here's the payoff. Basically, no more manual tuning or manual work. No thresholds to configure. You can optimize without any disruption. And basically, you have at the end performance up and cost down, right? And of course, a lot of stability during any different scaling events.
All right, we've talked about this. Let's see it. This is like too good to be true. Let's see how this works, Luis.
Perfect. Demo time. Okay, guys. Here I have my CastAI console where I can see all my clusters that are connected in the platform. To get started with CastAI is super easy and quick. You can connect your cloud, fetch. We can discover all of your clusters, or you can just install a quick agent, selecting your distribution. We support any Kubernetes distribution in the market today. In a few minutes, you are going to have a savings report showing the savings that you can have and which strategies you can use, right? This is very, very quick and takes like 5 minutes. Also have your agent in place in our cluster. I have here my GKE with 1.33. Here you can see all the metrics that we discussed today around provisioning, requests, the usage. So you can see all this over provisioning in real time, right? And specifically about workload outscaling, that's the main point for today. We have here in the menu the option workload outscaler. And here it's where the magic happens, right? You can see here in the above the percentage that we are expecting to reduce in the cost, all the CPU difference that we are expecting, or memory, right? And here you can see all the list of your workloads in your cluster with important data, right? For example, the savings estimated per month, which scaling policy do you want to use? So this is very important. You can customize the behavior that CastAI is going to have in your workloads. For example, setting different percentiles or thresholds. So it's very customizable. And here it's the difference between the requested and the recommendation, right? And here it's where you can turn on, turn off the automation, right? It's very, very simple. I have here real workload in my cluster, in my Kubernetes cluster, and a microservice that's called Resize demo, right? If we drill down here, we can see that this container is running from almost 2 hours. And if you describe here, we can see that we request 700 MIDI cores and 200 megabytes of memory, right? And if we see this here in the console, we can see exactly the same, right? 0.7 CPU requested and 0.195 megabytes requested, right? And here we can, CastAI shows you exactly all of the data, the difference between the requested, the usage, and of course the recommendation, right? And before just enable this to show the change without the restart, I will quickly show how customizable this is. This is the scaling policy. You can define which resources are going to be optimized. You can set some percentage thresholds and a lot of important constraints here. And now I'm going to just turn on. Let me put this here. I'm going to turn on the optimization here. Save changes. And we can see that the container was not restarted, still with 2 hours uptime here. And if we describe again this container, we can see that the request is for CPU and memory drop to 10 millicores and 10 megabytes. That's exactly what CastAI was recommending. And if this pattern start to change, for example, if we have a lot of traffic or someone generating load in our application, we're going to detect this and adjust automatically without any restart and any disruption.
That's
This is
pretty
cool,
cool.
right, Leo?
That's pretty cool. But we should talk to people about when restarts are important and when they're going to happen. So, like for example, if my resize requires more capacity than the node is capable of handling, I will need to evict the pod and restart it in another node, unless you're using CastAI's live migration feature. So going back to why platform is important, right? Like if I have to do a restart, it's much better to live migrate that pod off of the node than to forcefully evict it. Another place where I think restart might be very important is where we have contention. So you have noisy neighbor problem, which is the reason why most people use Kubernetes constraints very extensively is to avoid services impacting one another. And again, if you have CPU, network, or disk contention, the only way you can kind of alleviate that is to get either the victim or the culprit off of the node. Something that we'll cover in a future webinar around contention detection, another capability of the platform. So, Luis, thank you very much for demonstrating this in kind of the simplest terms. This is pretty cool. And I think now we should open this up for Q&A. What do you think?
That's perfect. Thank you, Leon. Let me
So,
go back here.
so Alexei, should we ask folks to raise their hands? Should we just talk through some of the questions in chat? And folks, if you want to speak up, I think we can unmute you if you want to ask any particular questions.
Absolutely. I think that we have one person who raised their hand. So we can unmute them.
I, yeah, yes. Let's go ahead.
So can you elaborate on the live migration thing that you mentioned when you need to basically you will not evict the pods and restart them on the separate node, but you said something about live migration. What is that?
Yes. Yeah. So that's a great question. Uh, 2 KubeCons ago, so not the one in Europe, but the one in North America. I'm forgetting already what city it was in. That's how blurred things are. We announced a capability for live migration within Kubernetes. So if you're familiar with vMotion in the VM world, if some of you guys will remember that, you're able to move a virtual machine from physical host to physical host without downtime or with very, very small amount of uh, unresponsiveness, like measured in sub-second. So we introduced that same capability in Kubernetes 2 KubeCons ago, and we're working with select partners right now. It's available as part of our platform. But essentially, what it lets you do is take a pod from node A and move it to node B without interruption of the execution cycles, and none of the TCP sessions, so your network connections, aren't interrupted either. So imagine you have a Redis server that's running, and maybe we should do another webinar on this just to refresh everyone. I think, Alexei, that's a great topic for us. But you can essentially move Redis or a Postgres database or anything else that's stateful or connection bound from node A to node B without a forced restart. And that's extremely useful for a lot of not only optimization cases, but for maintenance cases, for high availability issues that you might be experiencing, especially when you have legacy monolithic applications that weren't designed from the ground up for Kubernetes. You know, we tend to think of things as stateless microservices in the cloud native world, but that's not true for all applications. Sometimes you're faced with real world realities where restarts are extremely painful, and that's what live migration is intended to solve.
And the other was, so do we still need HPAs or something like that when you're using Cast AI, or HPA is completely out of the picture now?
No, it's not out of the picture. It's a great question. And other folks, like, please, thank you for the great question, by the way. And I'd love for others to chime in. You can use HPA in multiple configurations. So think about it from this perspective. And it can be a native HPA that Kubernetes gives you out of the box. You could use a wrapper like Kata, which gives you event-driven uh, horizontal autoscaling. You can use CAST implementation, which it doesn't matter, whichever is your preference. The benefit of using both, so if you read the HPA and VPA documentation, roughly speaking, the documentation says thou shalt never mix the two concepts. So if you're using horizontal scaling on CPU, don't use vertical scaling on the same metric. Why? Because you have two algorithms competing for the same objective function. So if you're using HPA for requests per second, that's great. Then you can use VPA for memory pressure, as an example. The way we treat it is a little bit differently. We think about horizontal scaling as the short-term average fix for your workloads. In other words, when you have a spike in your applications, vertically sizing is a slower way of achieving more capacity than horizontal scaling. So We want to, for spikes, both up and down spikes, we want to use horizontal scaling. And vertical scaling treats the long-term trend of the application and also takes into account some natural boundaries. Like if your app doesn't spike beyond one CPU, there's just no reason to give it two. It'll never help the situation. So horizontal for short-term bursts, vertical scaling or workload right sizing for long-term trend following. Does that make sense? Cool. And Gary, thank you for reminding me that it was in Salt Lake City, and now I do remember Salt Lake. We had a question from the audience around how does our solution compare to Carpenter? I want to address it. So Carpenter is a great tool. It's open source. You can read the source code and what it does. We have lots of our customers, or actually the vast majority on AWS, come to us with an existing Carpenter implementation. And you can keep your Carpenter implementation. That's fine. Our workload right sizing tool works great with Carpenter. But this is the objective of the platform where 1 + 1 is much greater than 2. So we beat Carpenter on average by 30 to 40% in objective cost results. But more importantly, there is a difference in scope in the way Carpenter works. It's a single cluster solution. So it thinks about one cluster at a time. We think about your whole estate. So just giving you an example, if you have reservations that you need to contend with, reservations, savings plan, you are going to have to code your instance preferences right into your Carpenter configs. Cast will take those into account. And even though there's a cheaper option available in the short term, we know that you have reservations to burn down. So I'm just giving you one small example. We're not going to give you the full scope of difference between Cast and Carpenter. The thing you should take away from this conversation is every one of our customers comes to us with a Carpenter implementation on AWS because they've started down their journey, and we show them how to work much more effectively and save even more money. But the fact that you've started down that path is amazing. Okay, we talked about live migration. We talked about these questions around Carpenter. Uh, Thoughts on how Cast AI differs from ScaleOps or KubeCost. So great questions. I think KubeCost was I'm not going to get into a tabular feature function comparison between the various solutions. I can just tell you operationally and logistically where we're coming from. KubeCost really started its life as an open source observability tool for cost. That's something that we give for free to anyone who signs up on our platform. So if you want cost observability, just sign up today and you've got it without having to manage Prometheus or anything else in your cluster. And I think KubeCost is now trying to evolve to some automation, but it's still in very early days of its life. Cast started its life as an automation company first. So we look at the world from an automation lens each and every time we build a capability. We don't look at the world as an observability problem. I personally think observability is the emperor's new clothing when it comes to today's cloud native environments, because the last thing you want is someone to tell you more things that you should do for your human engineers to execute. So recommendations are bad. Automated actions are great. And then from what I'll just mention, I think Scalps is a great solution for vertically sizing applications, and we do see them sometimes. We treat the problem as much more of a holistic optimization issue, meaning node scaling is important, cluster scaling is important, horizontal scaling is important, vertical scaling is important, detection of noisy neighbor is important, live migration of containers is important. That's the value of an overarching platform. And while you can string together as an infrastructure team, while you can string together a set of solutions that may or may not cover the functional requirements, like you can use ScaleOps for vertical scaling, you can use Carpenter for node auto scaling, you can use KubeCost for observability. You might not have a live migration solution, but you might decide, okay, I can't use that right now. You will have to probably build something else for contention detection or use constraints. But then who is the team responsible for stringing all of those solutions together and making them viably work as one platform? And the answer is it's going to be your infrastructure team that's responsible. And that's where we see the difference in our approach. Although all of these tools in the market are great and they're raising awareness, we think that our capability is addressing a platform-wide need, not a single point solution issue. Dobie asked, does our platform work with RPS? To the extent that you use Kata as a standard solution, yeah, you can use any custom metric to scale your workloads horizontally. In fact, I'll give you a little sneak peek. We have some customers that are using custom metrics to vertically scale, is specifically around memory. Yolanta actually worked with one of those companies. We can't mention the name, but a very popular vector database in the industry. And that was an interesting challenge because we had to look at the internal metrics that Go produces in order to understand the real usage requirements for Go. And we'll be doing similar things for Java metrics as well. All right. We have one more question regarding live migration. How do you handle persistent volume claims, which commonly get stuck for minutes when doing node migrations? Depends on the PVC type. So if you're moving block storage across, there's a requirement to stay in the same availability zone. If you're using EFS, for example, or the NFS protocol, that happens instantaneously. We can pause an application in the worst case scenario for several minutes without there being negative implications on the underlying TCP connections. Not going to go into the scope of how we do that in this call, but we've handled many use cases with PVCs, and it depends on the file system and it depends on the underlying storage, but it's very possible. Thanks, Sean, for that great question. Very insightful to ask about persistent volumes. Do we have any other questions? Anyone actually want to speak up a little bit? Use their voice? Okay. Luis, I think we have Alexei, we have another question here. How does resizing work with Java-based pods where JVM already pre-allocates the resources? Does the JVM in the pod need to be restarted? That's such a good question. Yolanta, do you want to take that one in the current and future state?
Yeah, of course. So one of the things we are working in parallel is better management of JVM memory. And one of those is being able to inject even environment variables with the configuration we feel that is more proper, like is the most proper. So yeah, I'm not sure about, we haven't tested this in like live scenarios, but yeah, we are working with being able to change internal Java parameters as well.
Yeah, so just for folks that aren't familiar with the internal details, it used to be in older versions of Java that you would have to use this parameter called XMX, which is the majority of the memory that Java takes for heap. And then the problem is that your pod looks like it's using all that heap. Like regardless of what you're actually using, Java pre-allocates all that memory. And then in newer versions of Java, they've made it so that whatever your container size is, the heap will just be roughly the size of the container, minus a little for the stack and other things, but roughly the size of the container. But it still doesn't solve the problem of how do you know how much memory you're really using in Java? And that's the problem we're trying to solve. And there are two important vectors there. If you give Java too little memory, then you risk overworking the garbage collector, which will force CPU cycles to thrash much harder. So why is that bad? It's bad because memory is much cheaper than CPU cycles. So if we're forcing the garbage collector to work much harder, that's not a good outcome. So we have to balance between making sure that we're not allocating too much memory for JVMs and also making sure that the JVM is not running the garbage collector hot, which is going to end up running you more expensive. The services will be more expensive at scale in the long term. And that's the problem that Yolanta and her team are solving right now. Stay tuned this quarter for some interesting announcements on that side. And do we have any other questions from the field? How does it deal with memory leaks?
Yeah, so about the memory leak, so there are, of course, a few ways to address it. So you can try to set global limits just to be safe. You can set workload level limits as well. But yeah, we have multiple protections. For example, we have some like reasonable sanity checks depending on the workload usage where we decide that it looks like a memory leak. The usage grows too fast, it consumes too much memory, and we put a cap on it. So one of the ways, and of course, like there are configurable cluster level and workload level memory limits for just being a sanity checks as well. But yeah, internally in the system, if the memory grows unreasonably, we try to detect those patterns and put a cap on it.
Mihao, I hope I pronounced your name correctly, or Michael. I can never get that soft L pronounced correctly. Could you elaborate on the local storage question that you have? Okay. I'm going to leave the local storage question for a second. The next question that Mihao has is it feasible to have feedback loop to verify reliability of workloads with decreased resources? i.e., would it be great to choose from a metric we examine behavior such as workloads with decreased latency, such as latency. So basically, we're reducing a resource. How do we know that it's running better or worse? And that's going to be a topic of a future webinar for a very exciting capability we're releasing called APA. I don't want to spoil too much right now, but this summer we're going to be unleashing a whole series around exactly this type of feedback loop.
Yeah, but probably one small thing to add, we are starting to leverage like PSA metrics to understand if the CPU for workload is being throttled and how much. So yeah, that's one of the things you can try to leverage just to detect if there's throttling and how much.
Yeah, Yolanta, that's a really good point. Thank you for reminding me. So in part of the platform, remember we talked about the platform play when Luis was presenting, we talked about noisy neighbor contention. So one of the negative behaviors you might see when you're too tightly bin packed on a node is you have two pods that are conflicting with one another. And the typical detection mechanism in Kubernetes is something called throttling, which is not a good metric for this purpose. Why? Because throttling just measures when requests approaches limits. And so that's an artificial throttle in that we don't believe in limits for CPU specifically, especially in the world of highly over-provisioned capacity. So we've introduced a new metric, which is unfortunately not available in KubeState. It's not something that you would typically get from a node exporter. It's called PSI, and you guys can look this up. It's called pressure stall indicator. That's what Yolanta was mentioning. And PSI measures you have to have a reasonably modern kernel, Linux kernel, but it measures whether your applications are actually waiting for a resource to be given to you. And that includes CPU. It doesn't include memory because memory is not compressible, but it also includes disk and it includes network. So if you're throttled for any reason because you don't have access to enough network, CPU or disk IO, this PSI metric will chime off. And then we have a module that actually separates, we call it busy node movement detection and remediation, that actually separates the workloads that are causing each other problems. So it's a topic for another conversation, but it's part of this whole workload right sizing mindset where you want to start thinking about things at runtime versus only shift left at design time because you'll inevitably over design your infrastructure if you try to capture all the edge cases in code, right? We are having a session at FinOps X We are sharing the recording, and Dobie has a question. With current Carpenter in one cluster, we are seeing frequent disruption of pods as it scales node rapidly. Do you see any scenario with Cast AI where we see more disruptions? Well, it depends when you're getting the disruption, Dobie. So, are you getting the disruption because of node consolidation? This is, I guess, what the Carpenter term is for bin packing, right? It's when you have two nodes that are somewhat underutilized and they bring the nodes together for consolidation. And yes, we hear that from Carpenter users all the time. In fact, most customers don't turn on node consolidation in practice because in production, because of exactly this reason that you're seeing. Our component for bin packing, and this is solving the same problem, works very differently than Carpenter. We run all of the pre-simulations before we decide that we're going to drain a node. There are many scheduling simulations we run to make sure that we're not being disruptive. And that scheduling simulation allows us to know, will the pods land on these other nodes? Because like if another node needs to be upscaled, there's no point in doing a consolidation, right? So it's called Evictor in our platform. And if you're having this pressure with Carpenter, I'd highly suggest that you book a demo specifically with two capabilities on the platform, Evictor and rebalancing. Because rebalancing solves this problem in a very different way. It uses what's called a green-blue deployment model that pre-creates a new set of nodes and then drains the old ones very, very carefully in order to get pods to land with minimized disruption. And that makes sure that your pod disruption budgets are adhered to. That makes sure that all of your topology spreads are working well. Basically, all of the constraints you have are fully supported before a single pod moves, and we make that rebalancing action take place. So Dobie, it's something that we can dig into more detail with you. All right, any other questions? I think these were way more questions than we were expecting from a usually quiet DevOps audience. Awesome. With that, let's go to our next slide, Luis, if you don't mind. And here's what we're asking you guys to do. Go to the Get Started page. You can use this QR code if you want. Try a platform for free. First of all, if you don't have observability in your clusters, go install it. It's free forever. Just get free cluster observability. Connect away as many as you want. And then if you actually want to try these capabilities, we're going to book a demo with you, walk you through it, and you can start using the platform today. So thank you guys so much for the great quality questions. We will make the recording available to you. Yolanta, thank you there for the real deep tech, being there for the real deep tech support on some of these questions. Luis, thank you so much for preparing the demo for us. And I want to wish everyone a very happy and fun Friday. Thanks, everyone.
Thanks, everyone.
Great. Thank you, everyone.